Hello, and welcome back to Shiksa da Costa. Today we're going to verify some properties of geometric figures. So today we're going to learn how to use algebra to check if those patterns that we noticed in geometry are actually true. To start us off, here is a triangle, and here I've given you the coordinates of the triangle, of the vertices of the triangle, plotted on a coordinate plane. What I'd like you to do is pause the video and do your best to find an equation of a circle that goes through all three of these points, sort of just like that. Find the equation of that, and then try to estimate or calculate what the exact distance is between the center of the circle and all of these 3 points separately. Okay, well, the origin of this circle is right here at the center, and the distance from here to point A is 25 units, right? And that's pretty easy to see. It's just the coordinates of A right here. If the origin is here, then that distance must be just the y value of 25. Now this is the radius of the circle, so I actually don't need to calculate the distance here using the formula for the line segment, the length of a line segment. Instead, I can just say, okay, if that's the radius, well, that's going to be the distance from the center of the circle to all points on the edge of the circle, including these 3. And this is sort of like what you might have seen earlier when we plotted 3 points of a triangle and we saw the right bisectors, and the concurrency point of that happened to be in the center of that circle. Here we verified that that circle actually does go through all 3 of those points. And we're going to go take that one step further. So let's take that one step further and actually algebraically verify that property of right bisectors. So find and graph the equations of the right bisectors of all 3 of these line segments, and then ask yourself, what do you notice? Pause the video here for as long as it takes for you to do that. Okay, well, just focusing on line AB first, right? The slope of line AB is found by taking the y values and subtracting those. That's the rise. And then the x values and subtracting those, and that's the run. And so that would be negative 32 is the rise, so going down 32 units and going across by 24 units. We can simplify that to just negative 4 over 3. Now, if I want to find a line that intersects this perpendicularly, the slope of that right bisector needs to be the negative reciprocal of this. So the negative reciprocal would be 3 over 4. To bisect the line, it does have to go through the exact center, the midpoint. And I can find that just by averaging the x values and averaging the y values. So if I were to do that, I would get exactly 12 and 9. And so I can plot that point right over there. And before I do that, let me just make sure that I'm going to graph the rest of the line really well. So if the line is y equals mx plus b, if I want to find out the y-intercept, I just have to isolate b. So if I subtract mx on both sides, the left side becomes y minus mx. The right side is just ends up being b. So the y-intercept here can be found by taking, or the value of b, the y-intercept, can be found by taking a y value, so that point that would be here of 9, and subtracting mx. M is the slope of the right bisector, and x is just the x-coordinate of that point. And that gives me 0. So the midpoint, which would be right over here, the line that goes through it at a perfect right angle has a slope of 3 over 4, and its y-intercept is 0. So that's right over here. So just using this point and this point, I was able to draw a nice straight line, and I know for sure that intersects this at a 90-degree angle. Now, to move on to BC and follow the exact same steps. First, I will find the slope of BC. Right? Just using the slope formula there, I'll see it's 1 over 3. And that means that the slope of the right bisector needs to be negative 3 over 1, or just negative 3. The midpoint can be found by averaging those x values and averaging those y values. And so I've got that midpoint coordinates right there. And then just using the same formula up here, I will find the y-intercept by taking y minus m times x. And that gives me, oh, actually it gives me 0. How about that? So if I plot the midpoint right here, I know that this goes through the y-axis right over here, so I can just put a ruler right there and draw that right bisector. Finally, for AC, the slope of the line is 3, so the slope of the right bisector would be negative 1/3. The midpoint can be found by averaging those x and y values, and that is those coordinates right there, negative 7.5 and 2.5. And I can use, again, the same formula here, b equals y minus mx. I'll plug in the slope, the y value, the x value to get 0. This also goes through the origin, just like that. And so the point of concurrency for all three of these right bisectors, they all seem to, this is the thing that I noticed, go through the origin, 0, 0. And if they do that, and I can actually draw a circle, or I can create the equation of a circle that's centered on the origin, I know that equation is x squared plus y squared equals r squared. The radius here is clearly 25 if I want to go through this point. And I can draw that circle, and I'll notice that that equation actually intersects all of the vertices of the triangle. I can plug 24 squared plus negative 7 squared. That does equal 25 squared. And negative 15 squared plus negative 20 squared, that also equals 25 squared. So all these 3 points satisfy the equation of the circle that's centered on the origin. And actually, the right bisectors of all 3 sides of the triangle also are concurrent at the origin. So to verify a geometric property, one thing you can do is just plot the vertices of that geometric figure on a coordinate plane, and then just use algebraic techniques like finding out the slope or the midpoint or the perpendicular lines to verify any property that you choose. And the algebraic techniques are so useful because they actually calculate the exact values, and we're not just relying on a visual diagram to confirm our property. Now, one thing to note is there are usually more than one technique to actually verify a property. And so please don't feel limited to just doing things the way that you're seeing maybe someone else doing it. If you figured out a way and it actually verifies that property algebraically and all your mathematics are sound, then that's great, man. Good for you. Here we're going to prove that the mid-segments of a quadrilateral formed by these 4 points actually form a parallelogram. So let's plot these points here, right? So I've colored them differently just so I could know which points are just by looking at that, right? So there's A, B, C, and D. And now that's the parallelogram that it would create. If I want to find the mid-segments, I need to connect the midpoints of the sides. So first I need to actually find out what the coordinates of these 4 midpoints are. And then I got to make sure that the sides created by that parallelogram, by those mid-segments, the parallelogram created by those, actually is a parallelogram. And here's how I'm going to do that. First, let's find the exact coordinates of this midpoint right here between A and B. And to do that, I can just average the x values and average the y values between A and B. Plugging those into the formula, I find out that the coordinates of this are 2.5 and 2.5. Easy enough. Moving on to the next midpoint, right, the one between B and C, I'll just use the same formula to find out that the coordinates are 3 and negative 1.5. Between C and D, the same formula tells me that the coordinates here are negative 1 and negative 1.5. And finally, over here between A and D, the coordinates are negative 1.5 and positive 2.5. So now that I've labeled those P, Q, R, and S, one way I can confirm that this is a parallelogram is if the opposite sides are parallel. So the slope of this line needs to be the same as the slope of this line, and the slope of this line needs to be the same as the slope of this line. So I just need to calculate all 4 of those slopes and compare those values. Between P and Q, I can find the rise and the run just by doing the slope formula. And I'll find out that the slope here is -8. So it's going down by 4 and going across by a half. And so that's a rise over run gives me -8. Between R and S, so this line over here, if I use the same formula, I actually do end up getting the exact same number for the slope. So these two lines are parallel because the slopes are identical. Moving on to P and S, or S and P, depending on whichever way you'd like to use that line segment, it doesn't really matter. The slope over there, I'm just estimating it's 0. Looking at the coordinates, I can see the y values haven't changed at all, so I think I am really expecting this to be 0, and yes, it is. Similarly, between Q and R, without even doing the slope formula, I can notice that the y values are the same, and therefore this will have a slope of 0, and just our slope formula will actually confirm that for us. So I can say that since the slope of PQ and the slope of RS are equal, these two line segments are also parallel. And since the slope of PS and RQ are equal, PS and RQ, the line segments, are also parallel as well. And because the opposite sides are parallel, PQRS is a parallelogram. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.